This research introduces an extension of constitutive artificial neural networks, CANNs, to capture inelastic phenomena, specifically plasticity, through the concept of inelastic constitutive artificial neural networks, iCANNs. Building on the existing CANN framework, which ensures physically reasonable predictions by considering constitutive constraints such as objectivity, material symmetry, thermodynamical consistency, and polyconvexity, iCANNs aim to accurately model plastic material behavior. The authors propose a formulation that includes the prediction of elastic and plastic Helmholtz free energies, the inelastic flow rule, and the yield condition defining the onset of plasticity. This formulation utilizes a combination of 4 feedforward networks and a recurrent neural network, leveraging the second Piola-Kirchhoff stress measure for training. The iCANN formulation is capable of capturing both associative and non-associative plasticity, as well as kinematic hardening effects, thereby broadening its applicability to a wider range of materials. To demonstrate the framework's capabilities, the authors train the iCANN on artificially generated data for perfect plasticity of von Mises type, tension compression asymmetry, and kinematic hardening. Satisfactory results are achieved with a single load case, and highly precise agreement is observed with an increased number of load cases. The performance of the specified iCANN is further validated using experimental data from X10 CRMUVNB 9:1 steel, trained on both uniaxial tension and cyclic loading separately, and then tested on the opposing set. The results demonstrate the autonomously discovered material model's ability to accurately describe and predict the underlying experimental data. The iCANN formulation offers a powerful tool for automated model discovery, machine learning, and constitutive modeling of plastic material behavior. By leveraging neural networks to capture complex material phenomena, this research contributes to the development of physically sound material models capable of predicting suitable material behavior even outside the trained data range. In addition, the paper introduces the concept of plasticity in materials, which refers to the irreversible deformations that occur after yielding. This phenomenon is attributed to various microscale effects, such as crystal dislocations in metals and relative movement of grains in soil mechanics, leading to different macromechanical phenomena, including tension compression asymmetry. The paper also discusses the development of novel material models that leverage machine learning approaches to accurately predict material behavior and failure mechanisms, addressing limitations of traditional methods and the increasing use of machine learning in computational mechanics. Constitutive Artificial Neural Networks, or CANNs, are introduced as a novel approach to modeling elastoplastic material behavior, capturing inelastic effects while adhering to material theory and thermodynamic principles. The authors develop a new class of CANNs, labeled iCANNP, specifically designed for plasticity. The underlying materials theory and thermodynamic principles are discussed, focusing on finite strains and stress definitions derived from elastic and plastic Helmholtz free energy definitions, ensuring thermodynamic consistency. Feedforward networks are designed for elastic and plastic Helmholtz free energies and plastic potentials, with specified network structures provided for numerical investigation. The performance of iCANNP is validated using artificially generated data of perfect plasticity and experimental data of X10 CRMUVNB 9:1 steel, demonstrating the importance of incorporating material theory and thermodynamics into machine learning architectures. The authors propose a novel, thermodynamically consistent, finite strain, isotropic, inelastic material model based on a correlated intermediate configuration, allowing for the computation of stress and strain-like quantities without rotational non-uniqueness. The Helmholtz free energy is introduced as an isotropic function of elastic and inelastic quantities, leading to state relations of the second Piola-Kirchhoff stress, relative stress, Mandel stress, and backstress. The isotropic volumetric decomposition is utilized, separating the deformation state into isochoric and volumetric components, resulting in new invariants for the right Cauchy-Green deformation tensor. The Clausius-Planck inequality is evaluated to derive constitutive equations, and the reduced inequality, dret equals gamma dp is greater than or equal to 0, is derived, ensuring thermodynamic consistency of the model. This novel approach offers a promising method for modeling elastoplastic material behavior in a general manner. The development of evolution laws for thermodynamic processes necessitates the fulfillment of inequality 8. To achieve this, a potential is introduced as a scalar-valued isotropic function of the thermodynamic driving force, leading to the evolution law in equation 9. The plastic multiplier, lambda, is defined through the Karish-Kohn-Tucker conditions, ensuring non-negativity and introducing the yield function, which encloses the elastic regime. The yield function is a convex function, and its boundary defines the plastic domain. The Helmholtz free energy function, psi, is derived from a scalar-valued function, which is affected only by stretches and not by rotations. It is formulated in terms of the right Cauchy-Green tensor and is an isotropic function of its arguments. The Helmholtz free energy is decomposed into isochoric and volumetric terms, ensuring polyconvexity, and is separated into elastic and plastic parts. The elastic part is described by equation 11, while the plastic part is related to kinematic hardening. The plastic formulation is further developed by introducing a pseudopotential to formulate the evolution of inelastic quantities. The yield surface is defined by the yield function phi, which encloses the elastic domain and defines the plastic domain. The yield function is described by a stress-dependent part and a parameter related to the initial yield stress. The yield function is formulated in terms of a potential H, gamma, as shown in equation 14. The Helmholtz free energy is multiplicatively decomposed into elastic and plastic parts, and the plastic part is related to kinematic hardening. The elastic and plastic formulations are restricted to depend only on the elastic and plastic terms of the right Cauchy-Green tensors, respectively. The energy is additively decomposed into elastic and plastic parts, following the structure given in equation 11. The plastic potential is formulated in terms of the relative stress, including the Mandel stress and internal variables, which account for kinematic hardening. The boundary of the elastic regime requires an isotropic function of its argument, which can be described in terms of its integrity basis. The choice of invariants, including the first invariant as hydrostatic pressure, the second deviatoric stress invariant, and the third as the direction and state of stress, is based on sophisticated formulations of inelastic potentials. The inelastic potential can be expressed in terms of a Taylor series, ensuring convexity by using subfunctions with convex activation functions. The additive formulation of the potential may lead to non-smooth intersections, which can be avoided using a smoothing technique such as norm regularization. The flow rule and hardening laws are described by the plastic multiplier and the derivative of a plastic potential with respect to its argument. The plastic potential can be defined similarly to the yield surface, and for associative plasticity, the potential is equal to the one of the yield surface. The flow rule can be defined by the plastic multiplier and the derivative of the plastic potential. Multisurface plasticity is used to describe the elastic regime more adequately, where the elastic domain is bounded by a set of independent, convex surfaces that may intersect non-smoothly. The elastic domain can be expressed by the inner domain of all yield functions, and the yield surface is defined by the set of all stresses such that at least one yield function is zero and all others are less than or equal to zero. The convex domain has a smooth boundary, but the intersection of the yield functions may not, which can be difficult from a computational point of view. The norm regularization is used to smooth the intersection of the functions, and the resulting boundary adapts to the initial surface while maintaining smooth intersections. The visualization of the norm regularization is shown in Figure 1, exemplifying the smoothing of the intersection of two functions. The plastic potential must be convex, non-negative, and zero-valued at the origin, ensuring a smooth surface. The flow rule and hardening laws are essential components of the plasticity model, and the multi-surface plasticity approach provides a more comprehensive description of the elastic regime. The authors propose a neural network-based approach for modeling elastoplastic behavior of materials, building upon the work of Adhikari et al., 2017. By approximating the elastic domain with a smooth domain, they define the evolution of plastic flow using a linear combination of subgradients, leading to conditions for plastic loading and consistency. The flow rule is expressed in terms of multiple potentials, with thermodynamical consistency proven by fulfilling the reduced dissipation inequality. Their neural network architecture, called iCANN, combines a recurrent neural network, RNN, with feedforward networks, FFNs, for the elastic energy and plastic potentials. The elastic energy is decomposed into elastic and plastic terms, with separate FFNs learned for non-associative plasticity. The authors define 4 FFNs: psi-E for the elastic Helmholtz free energy, psi-P for the plastic Helmholtz free energy, H for the plastic potential defining the stress-dependent part of the yield surface, and G for the plastic potential defining the inelastic strain evolution. The network architecture is designed to ensure polyconvexity, a crucial property in continuum mechanics. The elastic Helmholtz free energy is formulated as a function of the right Cauchy-Green deformation tensor, with a Taylor series expansion up to quadratic terms. The plastic Helmholtz free energy is derived similarly, with the plastic right Cauchy-Green deformation tensor serving as input. The feedforward network for the plastic potential is designed to fulfill similar requirements as the yield function in plastic evolution potentials. The relative stress serves as input, and the invariants are formulated from this input. The activation functions used are the absolute function, the natural logarithm of the hyperbolic cosine, and the hyperbolic cosine, which are continuous and differentiable. Here is the combined summary. The presented work focuses on a specialized constitutive neural network model for inelastic elastoplastic material behavior, restricting it to the class of incompressible material behavior. The complex potential function, G, gamma, is formulated as equation 22, comprising 18 terms with various activation functions, including absolute, natural logarithm, and hyperbolic cosine, involving input features I gamma 1, J gamma 2, and J gamma 3, paired with learned weights WG1, 1 to WG2, 18. These activation functions facilitate nonlinear interactions among inputs and provide norm regularization, P equals 1, ensuring convex and non-negative properties. Weights are scaled by the initial yield stress, sigma y0, allowing for physically meaningful interpretations of neural networks output. The model's implementation in the TensorFlow library is used for training and evaluating its performance using mean-squared error loss, specifically with a mean-squared error of differences between predicted and experimental stress values, MSE in equation 23. The Helmholtz free energy equations are specialized to an incompressible model with the incorporation of the Lagrange term, ensuring compliance with a class of material behaviors. The model's performance is evaluated using mean-squared error loss, and the results demonstrate the effectiveness of the proposed approach. The incorporation of the Lagrange term and the specialization to incompressible material behavior enable the model to capture complex material behavior. The use of equation 22 and the TensorFlow library facilitates the training and evaluation process. The work also discusses the importance of considering second-order deformation and the incorporation of hardening parameters, which are often neglected in material modeling. The proposed approach provides a more accurate and comprehensive understanding of material behavior, enabling the development of more realistic material models. The results of the evaluation demonstrate the improved performance of the proposed model compared to traditional approaches. The Constitutive Artificial Neural Network, iCANN, framework is extended to capture inelastic effects by incorporating an elastic predictor plastic corrector scheme, enabling the prediction of plastic material behavior. This approach involves an elastic trial step, which computes trial stresses and checks for plastic admissibility, followed by a plastic corrector step using a Newton-Raphson iteration to enforce plastic admissibility. The predictor-corrector scheme is implemented through a recurrent neural network, which takes the right Cauchy-Green tensor and plastic stretch as inputs and outputs the updated plastic stretch, stress, and plastic multiplier. The framework is validated through numerical results, demonstrating its ability to predict different plastic behaviors, including perfect plasticity, tension compression asymmetry, and kinematic hardening. Artificially generated data and real experimental data from Kowalewski et al. 2014 are used to train the iCANN, with the atom optimization algorithm and L2 regularization applied in most cases. The results showcase the effectiveness of the proposed framework in capturing complex material phenomena. The training data sets are generated using a classical incompressible Neo-Hoekian type material model with a von Mises type yield criterion. The material parameters used are micro equals 12.5 kilopascals, K equals 25 kilopascals, and sigma y0 equals 2 kilopascals. The model is trained on 5 different combinations of loading scenarios, and the predicted weights of the plastic potential are given in Table 1. The results show that with an increasing number of loading sets, the number of active weights decreased, and the predicted solution converged to the actual solution. The predicted yield surface is plotted in Figure 5, showing that the yield surface did not differ qualitatively. The stress-strain data and model prediction trained on 4 loading sets are given in Figure 6, A, 2, E, and the loss over the number of epochs is shown in Figure 6, F. The results suggest that a wider set of training data leads to more precise results, but an already sufficient solution was observed for a minimum number of training data. The iCANN model's capabilities and limitations in predicting yield surfaces for various material models are comprehensively analyzed. The model demonstrates excellent match with generated data across different loading conditions, including uniaxial tension, equibiaxial tension, uniaxial compression, shear, and cyclic loading. However, it struggles to capture tension-compression asymmetry in elastoplastic materials, even when trained on uniaxial tension and uniaxial compression data. The predicted yield surface resembles a von Mises-type surface, but fails to match the expected mean value between yield stresses in tension and compression. A novel neural network-based material model is proposed to address these limitations. Trained on a combination of uniaxial tension, uniaxial compression, and equibiaxial tension data, the model demonstrates improved performance in predicting the behavior of incompressible materials. The predicted weights for the yield surface indicate that uniaxial compression plays a significant role in reducing the total error. The model is further extended to include kinematic hardening effects, as described by the hardening term in Equation 30. The modified model is trained on uniaxial tension data and tested using cyclic loading, demonstrating accurate prediction of stress-strain curves and good alignment with artificially generated data. The model's predictive capabilities are showcased through its ability to extrapolate beyond the trained regime. The yield function of the predicted model is examined when trained on different combinations of uniaxial tension, uniaxial compression, and equibiaxial tension. Figures 7 and 8 illustrate the model's ability to accurately capture the yield stress given in the training set, even under different loading conditions. The study highlights the potential of neural network-based material models to capture complex material behaviors and predict their response under various loading conditions. The yield function of the predicted model, trained on uniaxial tension and uniaxial compression data, exhibits good agreement with the artificially generated data, as shown in Figure 9. The weights of the predicted yield surface, listed in Table 3, indicate a dominant von Mises-type yield surface, with Wg2, 5 being the most significant weight. The predicted hardening model captures the hardening behavior, as evident from the stress-strain curves and visualization of the initial and translated yield surfaces in Figure 10. The translation of the yield surfaces at point A is visualized in Figure 10d, demonstrating the backstress, chi, and the translated yield surfaces of the trained and predicted data. The model's performance is evaluated through the loss evolution in stress-strain curves, providing a comprehensive understanding of its capabilities. The visualization of the yield surfaces and their translation under loading conditions offers valuable insights into the material's plastic behavior. The experimental data of X10 CRMUVN B91 steel from Kowalewski et al. 2014 is used to investigate the learning and prediction capabilities of the iCANN model. The data is transformed to the right Cauchy-Green tensor and the second Piola-Kirchhoff stress, and then input into the network model. A pre-training procedure is employed to find initial weights close to the final solution, and the resulting weights are used as starting points for training the total elastic energy. The model is trained on both uniaxial tensile data and cyclic tension compression data, with the resulting weights given in Table A.6. The predicted data is visualized in Figure 11, showing a close match between the predicted and experimental data. The training results show that the model trained on cyclic loading data fits better to both datasets, but additional kinks are observed in the transition from elastic to plastic behavior, indicating the onset of yielding. The proposed Constitutive Artificial Neural Network (CANN) structure combines a recurrent network with 4 feedforward networks to model elastic and plastic Helmholtz free energy, inelastic potentials, yield surface, and plastic flow. This approach allows for the modeling of non-associative plasticity, requiring different numerical treatment, including return mapping algorithms. The model is evaluated using synthetic and experimental data, demonstrating accurate predictions and convergence to the exact solution with an increased training set. However, the current framework struggles to capture asymmetric yield functions, highlighting the need to adjust the error measure. The model is also tested on synthetic data with kinematic hardening, showing good agreement between predicted and experimental data. Experimental data from uniaxial and cyclic loads are used as inputs, demonstrating the effectiveness of the proposed CANNs in predicting realistic material behavior. The results are presented in Figure 11, which shows the stress-strain curves for uniaxial tension and cyclic tension compression tests. The comparison between experimental data and model predictions trained on uniaxial tension and cyclic loading demonstrates the effectiveness of the proposed approach. The loss curves over the number of epochs are also presented, showing the convergence of the model. The incorporation of plasticity theory into the class of intelligent crystalline neural networks, iCANNs, has shown promising results in predicting material models of new materials that undergo irreversible deformations. The predicted weights of the elastic Helmholtz free energy for perfect plasticity are presented in Table A.4, showcasing the results for different training sets. Table A.5 extends the analysis to perfect plasticity with tension compression asymmetry, providing the predicted weights of the elastic Helmholtz free energy for different training sets. Figure A.12 illustrates the stress-strain curves for uniaxial tension, equibiaxial tension, and uniaxial compression, trained on artificially generated data using the Schogel yield criterion. The curves demonstrate the accuracy of the iCANN framework in predicting material behavior under various deformation conditions. The tables on pages 37 and 38 present the predicted weights of the elastic and plastic Helmholtz free energies and the plastic potential included in the yield function, obtained from pre-training and training on experimental data. Table A.6 on page 37 displays the results of pre-training on uniaxial tension data, where the weights exhibit a range of values, with some being close to zero and others taking on larger magnitudes. In contrast, Table A.7 on page 38 presents the results of training on both uniaxial tension and cyclic loading data, revealing similar patterns in the weights, with some being close to zero and others taking on larger values. Notably, the weights corresponding to the plastic potential term G are consistently smaller in magnitude compared to those associated with the elastic and plastic Helmholtz free energies. The predicted weights capture the underlying physical mechanisms governing the material's behavior under different loading conditions, providing insights into the relative importance of different energy terms in the yield function. This is critical for developing accurate constitutive models of material behavior. The results demonstrate the effectiveness of the proposed machine learning framework in learning complex material behavior from experimental data. The appendix on pages 39 and 40 provides declarations, data availability, and a comprehensive list of references cited in the research paper. The authors declare their contributions to the paper and acknowledge financial support from the German Research Foundation. The references cover a wide range of topics, including machine learning, artificial neural networks, and constitutive modeling of materials, demonstrating the author's comprehensive review of the literature. The references include classical works on plasticity, viscoelasticity, and finite elasticity, as well as recent advancements in the field. This research paper presents a novel thermomechanically coupled constitutive model for semicrystalline polymers, leveraging deep learning techniques to capture intricate material behaviors. The proposed approach integrates both mechanical and thermal aspects of material behavior under various loading conditions, enhancing predictive capabilities in material simulations. A comparative study involving different neural network architectures is conducted to assess the efficacy of the new model against existing approaches, providing insights into its performance and limitations. The paper also explores the use of automated model discovery using symbolic regression, demonstrating its potential in identifying the best model and parameters for human cardiac tissue. This automated approach can significantly streamline the process of material modeling, reducing the need for manual tuning and improving the efficiency of simulations. Moreover, the paper discusses the importance of incorporating thermodynamic principles in macroscopic models for stress-driven anisotropic growth in bioengineered soft tissues. It emphasizes the significance of considering both mechanical and thermal effects when modeling complex biological systems. In addition, the paper provides a comprehensive overview of various mathematical models and algorithms used in computational mechanics, focusing on viscoelasticity, plasticity, and damage modeling. It highlights the role of physics-informed neural networks for solving forward and inverse problems in mechanics, as well as the application of neural ordinary differential equations for data-driven anisotropic finite viscoelasticity. The paper also reviews the historical development of strength theories for materials under complex stress states, emphasizing the importance of anisotropy in material behavior. It touches upon the numerical characterization of uncured elastomers using a neural network-based approach and concludes with a discussion on the use of reaction diffusion models for Alzheimer's disease, combining PINNs with symbolic regression to identify potential mechanisms driving the progression of the disease.